Dear students, now let us start the next chapter, forced vibration. Today's topic is equations of motion with harmonic force. I, Dr. Balraj Singh Brad from Yadavindra College of Engineering, Talwandi Sabo, India, am lecture. Forced vibrations due to the external excitation. In the forced vibration systems, the amplitude of vibration is almost constant due to the application of external forces. For example, ringing of electric bell. We get a ringing sound from an electric bell when the electricity is on. As long as electricity is on, ringing is there, amplitude is constant. Once the electricity is switched off, then only vibrations subside. Similarly, in certain machine tools, we have electric motors which are operating the machine tool, or sometimes during machining when we apply a depth of cut and give a feed, the machine tool vibrates. As long as the process or external excitation which is causing the vibrations is there, vibrations are there, and amplitude is almost constant. So in the forced vibrations, the amplitude of vibration over a longer span of time is constant. Whereas in the case of free vibrations, vibrations are there for small time periods and they continuously go on losing the energy and amplitude reduces and it goes on reducing and it approaches and the system approaches the equilibrium position very soon. The external force which keeps the system vibrating is called the external excitation. So in the force vibrations, say spring mass system with an external excitation is subjected to force vibrations and identified as that amplitude of vibrations will be constant. The external excitation may be a periodic one, harmonic or non-harmonic. We will be focusing on harmonic external excitation, which can be represented by sine or cosine curves. It can be impulsive external excitation or a random in nature. Vibrations due to impulsive forces, some sudden impact of energy, are there for a small period of time, are transient in nature, and slowly they die out. Sometimes we do not know the source and type of excitations, and external excitations are random excitations, as is the case of the seismic vibrations due to the earthquake. In the machine systems or structures, there are various sources of excitation. External excitation in the dynamic vibration systems we can identify easily. As we discussed, it can be due to certain machining operation, it can be due to some power drive or any other kind of say IC engine, some unbalance in the system. So we can predict this. But there is another excitation which is internal in the system. It is mainly due to unbalance. For example, due to the thermal effects, the different metals may expand or contract to different extents, resulting in the changes in the shapes and which produce an unbalance in the machine system, which continuously gives the vibration to the system. Moreover, due to heating, there are different heat transfer rates in different parts, so they result in different expansions and ultimately the excitations. When a system is subjected to resonance, resonance can be due to a random excitation or maybe due to some internal defect. Whenever resonance is there, natural frequency of the system matches with the frequency of external excitation, and we observe very large amplitudes which are very detrimental for the system. Sometimes loose or defective mating parts in the machine assemblies continuously produce excitations in the system. Similarly, coupling misalignments or defective assembly of parts may result in internal excitation. Bent shaft produces unbalance in the system, and these bent shafts are very much prone to failure at the critical or whirling speed of the shafts. In the bearings or journals, there can be defects like loose parts, improper clearance, surface roughness, out of roundness, and excessive play of shaft, which may give rise to unbalance in the system in the rotating shafts, which ultimately result in the generation of excitations in the system. We know for IC engines, the turning moment continuously goes on varying over the different strokes, and this periodic nature of the torque or the turning moment gives rise to unbalance in the system, so which is an external internal excitation. Similarly, in the punching presses, impact forces are generated. So, and these result in the unbalance in the system, which is a cause of internal excitation. Sometimes we have a motor to that a flywheel is attached, but to the flywheel there is a certain unbalanced mass attached, and when these unbalanced masses are rotating, they continuously produce unbalanced centrifugal forces, resulting in the imbalance of the system. Magnetic effects like stray magnetic fields may affect the working of the machine and may produce the unbalance in the systems. So these are some of the sources of excitation which result in forced vibrations of. For the spring mass damper system, mechanical vibration system with harmonic force, F is equal to F naught sine omega t. F naught is the amplitude of the external excitation. Omega is the frequency of the external excitation. Spring having stiffness K Newton per meter. Damping coefficient Newton second per meter. Mass in kg. Let at any instant mass is away from the equilibrium position by distance x taken downwards positive and is still moving away means downwards with the velocity x dot. Then we make the free body diagram of the mass. We mark all the external forces, spring force kx, damping force Cx dot, external force F, which is F naught sine omega t. Then, according to D'Alembert's principle, if we apply inertia force mx double dot mass into acceleration in a direction opposite to the direction of motion is downwards, so we apply it upwards. Then the system comes in static equilibrium. So by marking the forces in as we have shown in the figure, system becomes in static equilibrium, and we can make use of it in the coming slides. Let us find the equation of motion for force vibration system. This is the free body diagram as discussed in the previous slide. Now this system is, according to D'Alembert's principle, is in static equilibrium. So equilibrium equation is inertia force acting upwards. We have taken downward direction as positive, so upward is negative. So it is minus mx double dot is the inertia force. Mx double dot is the inertia force. C minus C, this Cx dot damping force, again minus Cx dot damping force. Kx again negative acting upwards spring force minus Kx is equal to F naught sine omega t external excitation acting downwards. Rearranging the terms, we get the equation, differential equation of vibration of a forced vibration system with damping. The general solution of the second order differential equation with the constant coefficients is x is equal to xc plus xp, where xc is complementary solution and xp is particular solution. So differential equation for a spring mass system with external excitation harmonic force is mx double dot plus cx dot plus kx is f naught sine omega t, and solution is sum of complementary solution and particular solution. Now let us solve complementary solution xc. Xc is the solution of the homogeneous equation mx double dot cx dot plus kx is equal to 0 according to mathematics, and this is the equation of damped free vibrations, and its solution we can write in the form of xc complementary solution e raised to power minus zeta omega t a cos under root of 1 minus zeta square omega t plus b sine under root of 1 minus zeta square omega t with two constants a or b. Or we can write it in terms of xc complementary solution c e raised to power minus zeta omega t sine and root of 1 minus zeta square omega t plus phi 1. Here again two constants, one c which is attached with the amplitude, and amplitude is varying, exponentially decaying, and phi 1 is a phase difference. Similarly, we can write it in the form of cosine terms, and constants d constant changes to d, and phase difference is phi 2. So either of these equations we can use to find the solution. So complementary solution is calculated from this equation of damped free vibrations, and the solution is like this, and its plot will be like this. Plot shows that the amplitude is decaying exponentially over the time, and after some time it is valid for initial seconds only, or say minutes, and after a small period of time it vanishes. This vanishes. So this solution, complementary solution, vanishes after some period of time, and we can use either of these equations. Next, particular solution. Particular solution is xp. We can assume particular solution to be of the form xp a sine omega t minus phi. Because from the observations we know that for forced vibrations the amplitude remains almost constant. So we have taken XP solution is of the form like this. Amplitude remains, amplitude A remains constant for any number of cycles, and T is quite large. For our applications, say a machine is operating for hours, days, or even a larger period of years. So over that period, amplitude remains constant. Now omega. Omega is the frequency of vibration of this solution. Because it is being forced to vibrate at this frequency, so it is same as that of frequency of the forced vibrations. So frequency or the time period for both the problems, for both the plots of the solution and of force, upper plot is of forced vibration, f is equal to f naught sine omega t, where the amplitude is f naught and omega is the frequency, so time period is 2 pi by omega. Similarly, the time period of particular solution is also 2 pi by omega. Only thing is amplitude is A to be determined and the phase difference is phi. The system will be vibrating with the lag of phi, from the vibrations of the external excitation. So this is the solution which we have to find out. Now we have assumed that solution is of the form xp a sine omega t minus phi. A is to be determined and phi is to be determined. A is the amplitude of the vibrations, phi is the phase difference by which it is lagging from the external excitation. Differentiating velocity xp dot becomes omega A cos omega t minus phi. Now changing cos to sine, so it is equal to sine pi by 2 plus this angle is equal to cos this. So we have got this solution. Similarly, again differentiating acceleration xp double dot is omega square A sine omega t minus phi plus pi. Here omega is the amplitude of vibration of velocity and omega square is the amplitude of vibration of acceleration. Now differential equation for forced vibration we know is mx double dot plus cx dot plus kx is f naught sine omega t. Let us put the values of xp, xp dot and xp double dot here. So if once we put the values, so this is xp double dot acceleration omega square a from the relation m omega square a sine omega t minus phi plus pi. C, this is the velocity of the particular solution, c omega a sine omega t minus phi plus pi by 2 plus k, and this bracket term is particular solution xp a sine omega t minus phi, and this is the external excitation f, which is f naught sine omega t. Now taking omega square term out, we have got m omega square is the amplitude of inertia force and got sine omega t minus phi plus pi. C omega A is amplitude of damping force. Sine omega force, the amplitude is C omega A, and sine omega t minus phi plus pi by 2. Ka is the amplitude of spring force, sine omega t minus phi. F naught is the amplitude of external excitation. So this term is inertia force, damping force, spring force, and harmonic force. These four forces are in equilibrium by this equation. Then we draw the vector diagram for force vibration system with damping. We had a solution. We had a solution in which we have inertia force m omega square a sine omega t minus phi, and damping force c omega a sine omega t minus phi pi by 2, and spring force Ka sine omega t minus phi, and external excitation minus F naught sine omega t is equal to 0. They are in static equilibrium. So when we make vector diagrams, these should make a closed diagram. Now, first of all, we will be drawing the external excitation. Let at any time t, the angle turned by external excitation is omega t, any general angle. We took a reference and we took omega t, is the any angle turned. So we have got F external excitation with amplitude of F naught. Then we draw spring force. Spring force has amplitude of Ka, but it is lagging from sine omega t, it is lagging by sine omega t. Phi is the phase difference. So we don't know the value of phi. So say spring force Ka is lagging phi by phi phase difference from the external excitation. So this Ka shows the spring force. Then damping force has a amplitude of C omega A, and from the spring force angle omega t minus phi, it is advancing by pi by 2. So this is a right angle, so it is advancing, and it is advancing than the spring force, so the direction is by pi by 2. So C omega A is the damping force. Then inertia force M has an amplitude of m omega square A and is advancing from the spring force by pi. Means inertia is always opposite to the spring force. So direction of this from here, direction of inertia force is this, amplitude is m omega square A. When we make a vector diagram, it is closed diagram like this. Let us draw a line parallel to damping force here. Let us make construction. Let this point is OA and this is B. Now from the triangle OAB, applying Pythagoras theorem, hypotenuse F naught square is equal to base OA square plus AB square. This is the observation, and tan phi is equal to perpendicular of the triangle OAB BA or AB divided by base OA. AB by OA. Now OA value is spring force magnitude Ka minus damping force. It is spring force magnitude Ka minus damping force magnitude m omega square A. This gives OA. OA is Ka minus m omega square A. And AB is equal to C omega. AB is equal to C omega. So, first relation F naught square is equal to OA square plus AB square. We will make use of this relation to find out amplitude A of vibration. And phi, this relation tan phi AB by OA will give us the phase difference. So in the coming slides we will calculate amplitude of vibration of particular solution A from this equation and phi from this equation. We know OA and AB. Next is determination of, as discussed, amplitude of vibration of the particular solution XP in this A sine omega t minus phi. Let us determine A. From the previous slide, we know F naught square is OA square plus AB square. F naught is amplitude of external excitation. OA is Ka minus m omega square A, and AB is C omega A. Now let us put the values of OA and AB respectively here. OA and AB, we get F naught square is Ka minus m omega square A, its whole square plus C omega A whole square. We take A square and A square common, so relation becomes A square minus K minus m omega square its whole square plus C omega whole square. Now, from this, rearranging the term, A becomes, and taking the under root, F naught by under root of the term K minus m omega square whole square plus C omega whole square. Now dividing the numerator and denominator by K, numerator becomes F naught by K, and in the denominator we get 1 minus m omega square by m omega square by K, where we know omega n is the natural frequency is under root of K by m. We put K by m values to be omega n square, and we get 1 minus omega by omega n whole square and its whole square plus C omega by K whole square. Now C omega by K, we divide C by Cc and multiply by Cc. C by Cc into Cc by K into omega. C by Cc is damping ratio zeta. In some books it is denoted by epsilon. So C omega by K becomes zeta, and Cc is critical damping coefficient. Its value is 2 times under root Km by K. So when we will solve this, this will become 2 under root m by under root K. Again, under root m by K is From this we will substitute, it will become omega n. So on simplification, if C omega by K becomes 2 zeta omega by omega n. We put this value of C omega by K here, and the answer A becomes F naught by K. We substitute F naught by K as Xs. It is zero frequency deflection. It is as if the external excitation is not vibrating. We have applied external force of F naught, static force. Then static deflection will be simply F naught by spring stiffness. So Xs is zero frequency deflection or static deflection. We substitute F naught by K by Xs and C omega K by 2 zeta omega by omega n. Then the solution becomes, amplitude is now known. It is Xs, zero frequency deflection, divided by, this is known from F naught by K. It is already known. Xs is known and F naught is known. K of stiffness of spring mass damper system is known. Omega external frequency is known. Natural frequency is known. Zeta damping ratio is known. Omega n is known. Now ratio omega by omega n ratio is also termed as frequency ratio, and sometimes in some problems, kindly note, it will be represented by R. It is frequency ratio to make the relation simple. So we know A is a function of static deflection, a frequency ratio, and damping ratio. So A has been determined. Then determination of phase difference phi for the particular solution xp is A sine omega t minus phi. Now let us determine this unknown phi. From the, as discussed in the vector diagram, tan phi is AB by OA. AB is Ka minus m omega square A. K is spring force minus inertia force. AB is equal to damping force. Let us substitute the values of OA in the denominator and AB in the numerator. We get tan phi C omega A upon Ka minus m omega square A. A will cancel out in numerator and denominator. We will divide the numerator and denominator by K. Numerator will become C omega by K and denominator 1 minus omega by omega n square. Now, how's omega by omega n square? Because m by k will be substituted from this relation. M by k is 1 upon omega n natural frequency whole square. We will substitute and omega, but then we will get this term in the denominator. This term is, as discussed, is the frequency ratio. C omega by k in the previous slide we have determined is 2 zeta damping ratio, omega frequency of external excitation to natural frequency. We will put in the numerator, we will solve, and tan phi becomes 2 zeta omega by omega n by 1 minus omega by omega n whole square. Now, for the spring mass damper system, we know the damping ratio, we know the frequency of external excitation, we know the natural frequency, we know the frequency ratio. So, phi will be determined using this relation. Two unknowns A and phi have been determined for the particular. Now, complete solution of force vibration system with damping is Xc plus Xp. Xc is the complementary solution. We will put it here, any of the three relations. Xp is of the form A sine omega t minus phi. A we have determined to be excess static deflection by under root of 1 minus omega by omega n. This is frequency ratio whole square, then its whole square, 2 zeta damping ratio, omega by omega n frequency ratio, this term whole square. We substitute phi from this relation, which will become tan inverse of 2 zeta omega by omega n to 1 minus omega by omega n whole square. Then once we have found xp, we will put it here. When we will put x and xp values, the solution will become x complete solution is c e raised to power minus zeta omega t sine and root of 1 minus zeta square omega t plus phi 1 plus xs sine omega t minus phi 2 1 minus omega by omega n whole square, its whole square plus 2 zeta omega by omega n whole square. So we have found the complete solution for the force vibration system with damping for a single degree system. Now we know total response is x is c e raised to power minus zeta omega t sine 1 minus zeta square omega t plus phi 1. This is transient vibration, which is there for initial period only, a small period only, as is shown in this plot. Complementary solution is valid for initial period and its amplitude is decaying and vanishes after some time. The second part is particular solution. Amplitude is excess by under root of this term 1 minus omega by omega n whole square, its whole square plus 2 zeta omega by omega n whole square, and it lags from the external excitation by a phase difference of phi. So we have this particular solution. This is a steady vibration. This second plot is xp particular solution. This is steady for the period of vibration under the external excitation, and amplitude remains constant and is A. So this is steady vibration. When we superimpose first and second plots, the complete solution x is equal to complementary solution plus particular solution. So we superimposed. So the complete solution is, for initial period, it is like this. Here, this part up to here, this shows that we have a transient vibration. This is up to here transient. Then onwards, the transient vibration has vanished. We have only steady vibration. So for the most of the applications, we operate for higher time periods. We need not bother about the initial period. So the only solution which is sufficient to solve the forced vibration problems is X is xp, or xp is A sine omega t minus phi. So, concluding, for the forced vibration with damping with harmonic force, F is equal to F naught sine omega t. System vibrates with this plot. This is the complete solution. X is complementary solution and XP. For the initial period, complementary and particular solution yield a red plot. After some time, complementary solution vanishes and we have only particular solution XP, which is valid for most of the problems because time period in for actual problems is large and only solution XP is sufficient to give reasonable results. The external excitation has been plotted as F is equal to F naught sine omega t like this. We observe that time period for both the vibrations is same. Only difference is the system mass will be vibrating with the phase difference phi and amplitude A. Amplitude A we have calculated in all the problems. Thanks, my dear students.